Hey guys, in this video we're going to learn how to graph a quadratic function that's in vertex form, and both given functions will have a horizontal and a vertical shift. So let's take a look. So whenever we graph quadratics, we always want to compare it and how it looks visually compared to the parent function. So this is our parent function, and we're going to use the same x coordinates for all three functions that are given. So we're going to use -4, -2, 0, 2, and 4. So then we're going to get our y values for our parent function. So when x is -4, we get 16, 4, 0, 4, and 16. So again, if you're wondering how we get these values, we substitute in our x value into the function of x squared, and then we simplify from there. And now to our right on our graph, we're going to plot all these points of our parent function into the coordinate plane, or onto the coordinate plane. And our first set of coordinates, -4, 16, again, we can't see where that's going to plot because our graph only goes up to 4, but it extends beyond. So kind of keep in mind the shape of the graph when you connect all your points. But we can graph -2, 4, which is right there. Our 0, 0, which is our vertex, and then 2, 4, and then we can't see 4, 16 on the coordinate planes, but we know it's going to shape how our parabola is going to shape with the fact that we have our point at 4, 16 way up there. So let's connect all of our points and then draw our arrows to indicate that yes, we have more points that go beyond the ones that we just graphed. Now let's take a look at f of x equals quantity x minus 2 squared plus 1. And we're going to take this graph and we're going to see how it compares to our parent function. We're going to use the same x values, -4, -2, 0, 2, and 4, to get our corresponding y values. So how we're going to do this, we're going to take our -4 and we're going to substitute that into our function, just like so. So if you notice, the x is replaced by -4. I should have also replaced the x here with the -4 as well for notation purposes, but so if we simplify the expression, or the equation, excuse me, -4 minus 2 is -6 squared plus 1. So then that simplifies into 36 plus 1, so we get 37. So if you look at it, -4, 37 is going to be very difficult for us to even graph onto the coordinate plane, but we can tell right away that it's going to be way, way, way past the 16 mark from our parent function. So we're going to do the same thing with our x value of -2, and we should get 17, 5, 1, and 4, or I'm sorry, 5. One thing I do want you to make sure that you do when you graph these points is you want to ignore all of these parent function y coordinates, and you're looking at the -4, 37, -2, 17, 0, 5, 2, 1, and 4, 5. So now plotting those points onto the coordinate plane, -4, 37 is way up there, so we're going to skip to the next point, which is -2, 17. That doesn't help us in terms of being able to plot it. If you had a bigger coordinate plane, then that'd be possible, but as of right now, again, keep in mind where it's going to be located on the coordinate plane. We can graph 0, 5, and 0, 5 is going to be right about there, so we can kind of pretend there's a 5 hash mark up here, and then we have another point at 2, 1, and then it looks like it goes back up to 5 when we have our x coordinate to be 4, so we're going to go graph 4, 5, and connect all of our points, and then draw our arrow. So it looks like the shape of the graph is pretty much the same, but there's an exact shift of our vertex from the original 2 units to the right and 1 unit up. So when we're comparing our functions with the parent function, you want to really focus on the size of our parabola, if it's a lot, or I guess if it's vertically stretched or vertically compressed. But in this case specifically, our vertex we're talking about is there is a shift to the right 2 units and up 1 unit. So we have a vertical shift of 2 units to the right and 1 unit up. And I can see that from my equation right when I started the example. If in the parentheses we have a -2, we have the x minus 2, you have to think about the opposite direction. So because we're subtracting 2 from the x inside of the parentheses, that means that our vertex is going to move to the right 2 units from the origin. and then the plus 1 at the end of the function lets us know that we are going to go up 1 unit on the coordinate plane from the origin. Now let's take a look at the function of g of x. G of x equals the quantity of x plus 3 squared minus 2. So we're going to use these points again, -4, -2, 0, 2, 4. And keep in mind, when we use these points, I just randomly picked these points as a standard. These aren't the only points that you could use. You can use -3 that goes in between -4 and -2. You can use -1, 1, 3. I mean, using your graphing calculator will help you get a better idea of what points that you would want to use. And you'd want to use integer values to get a clear point on your coordinate plane. So again, just using these points for our example, when we substitute -4 into the function, we get a -1, -1, 7, 23, and then 47. So my point is that when we graph this, I don't want you to think that there aren't any more points, because you'll take a look that, well, we can't graph 223 or 447 because that's going to go way off the grid. So we have to really focus on the 3 points that we have and kind of see how it's going to shape out. So if I graph these points really quick, here's -4, -1, we have -2, -1, and then we have 0, 7 that's way above the 5 that's off the grid. So if you look at it, when I connect my points, I don't want to just connect straight across from -1 to -1 all the way up to +7. I do note that I can actually, by this time, look at my equation and know where my vertex is going to be. If you look at the parabola on the right that's in red, we had a horizontal shift to the right, 2 units, and 1 unit up from the origin. Right there. So here it looks like we have a turning point somewhere in between here, but we don't know exactly where it's at. And we know that it's going to be opening upward because we have another point that's up here, up by the +7. So looking at the equation alone, I can tell you that my vertex is going to be at -3, so it's the opposite of what's in the parentheses, -3, -2. So then if I plot that into my coordinate plane, that's where my vertex is. There's a vertical shift 2 units down because of the -2 at the very end, and a horizontal shift to the left 3 units because the opposite of adding 3 would be moving to the left 3 on the coordinate plane on the x-axis. So now I can connect all my points, and you can see that we've shifted the entire parabola to the left 3 down 2. Drawing my arrows to indicate that the points do or could connect if I extended my graph. So don't think that it's just going to be like a J looking type of curve. It's going to actually be a parabola if I had more coordinates to actually plot here. So now when I'm describing my my shift, I'm always going to compare it with the parent function. So the blue parabola has a vertical shift 3 units to the left and 2 units down. So based on our 2 equations, we can tell that we have we can tell when a parabola has a horizontal shift and a vertical shift, and more importantly, we know where the vertex is by just looking at our equation. So again, in the parentheses, if it's a negative anything, the vertex is going to lie on the positive end of the x-axis. And then from that point, you go up or down depending on if you're adding or subtracting to that actual function. So to recap, the f of x's vertex is at +2, +1, and you can see that from the graph. And our g of x's vertex is at -3, -2, which is right there. Thanks for watching, guys. Make sure you do annotate and listen and write down anything that makes sense to you, doesn't make sense to you, so we can talk about it in class and have a productive conversation. Have a good day.